Dear students, today we will discuss one of the most important spectroscopic techniques that is commonly used for the structural elucidation of compounds, and that is NMR spectroscopy. In this video, we will have an introduction to NMR, a description of nuclear spin states, and how quantum theory explains the origin of NMR spectrum. So, what is NMR? It is also known as Nuclear Magnetic Resonance Spectroscopy. As the name implies, NMR deals with the magnetic properties or the spin properties of nuclei and how they interact with electromagnetic radiation in the presence of an applied magnetic field. And we know that in all forms of spectroscopies, the matter will interact with any of the components of the electromagnetic waves. Similarly, in NMR also, the molecule or the nuclei interact with the radio frequency waves of the electromagnetic spectrum. So we can say NMR spectroscopy is a spectroscopic technique which involves the study of transitions between the spin energy levels of a nuclei in an applied magnetic field by absorption of radiation in the radio frequency region. Before going to the theory of NMR spectroscopy, let's discuss about the nuclear spin states. We know that an electron is a negatively charged species which rotates about its axis and possesses a property called spin. And the spin nature of electron was determined by Stern-Gerlach experiment. Similarly, certain atomic nuclei also possess the property of spin. That is, the atomic nuclei can rotate about an axis and thus possess the property of spin. Nuclei means it consists of both protons and neutrons. Since a nuclei is positively charged, a spinning nuclei will also generate a magnetic field, and such a nuclei can behave as small bar magnets. All atomic nuclei which possess a nuclear spin will have a spin angular momentum vector I. In the case of an electron, the spin is determined by a spin quantum number represented as S. In the case of a nuclei, the spin quantum number is represented as I. For electron, the spin quantum number S is either plus half or minus half. But in the case of nuclei, the value of the spin quantum number I may be an integral value like 1, 2, 3, etc. Or it can be a half integral values like 1 by 2, 3 by 2, 5 by 2, etc. And even it can be 0. That is, if the spin quantum number I equals 0, then that means there is no spin angular momentum. So a nucleus, similar to electron, has the property of spin, and since nuclei are positively charged, they will generate a magnetic field on spinning, or nuclei will behave as small bar magnets. And all nuclei that possess a nuclear spin will have a spin angular momentum, and the value of the spin quantum number I may be integral, half integral, or 0. Each proton and each neutron will have a spin 1 by 2, similar to that of electron. And the total spin of a nucleus will be a vector combination of p plus n spins, where p is the number of protons and n is the number of neutrons. And this spin is determined by the parallel or anti-parallel alignments of the nucleons. That is, whether the spins of the protons and neutrons are aligned parallel or anti-parallel. Here is a table which shows the relationship of the spin quantum number to mass number and atomic number. So this helps us to predict the spin quantum number of a particular species by just looking at the mass number and the atomic number. So here, if the mass number is odd and the atomic number is either odd or even, then it will have a half integral value of spin quantum number. That is 1 by 2, 3 by 2, 5 by 2, etc. For example, 1h1, 6c13, 9f19, etc. In all the cases, the mass number is odd, whereas the atomic number may be either odd or even. So such species will have the spin quantum number value half integral values, that is 1 by 2, 3 by 2, etc. Now, if the mass number is even and the atomic number is also even, then the spin quantum number is 0, that is I equals 0. So in such a nucleus, all the spins are aligned in opposite directions or all are paired up so that there is no resultant spin or the net spin is 0. For example, 2He4, 6C12, 8O16, etc. Both atomic number and mass number is even. And the last is if the mass number is even and the atomic number is odd. So such species will have the spin quantum number as integral values 1, 2, 3, etc. Example 1H2, 5B10, 7 and 14, etc. These are a set of empirical rules to predict the value of the spin quantum number by relating the mass number and the atomic number. Now only a nucleus with the spin quantum number I greater than 0 will have a characteristic magnetic moment. And the magnitude of the spin angular momentum of a nucleus is given by vector I equals root of I into I plus 1 into H cross, which is equal to root of I into I plus 1 into H by 2 pi, where H is the Planck's constant. The angular momentum vector I can have two I plus 1 components along a particular direction, and normally all these components are degenerate. When we say the vector I can have two I plus 1 components, that means the number of spin states is equal to 2I plus 1, where I is the spin quantum number. And the values can range from mi equals minus I plus 1, etc. up to I minus 1I. For example, consider 1H1, a proton. For a proton, the spin quantum number I equals 1 by 2. Therefore, the number of spin states is equal to 2I plus 1. So that is 2 into the spin quantum number 1 by 2. 2 into 1 by 2 plus 1 equals 2. So that means a proton will have two spin states. One is plus 1 by 2 and the other is minus 1 by 2. Similarly, consider 1H2, a deuteron. We have I equals 1. So the number of spin states is 2 into 1 plus 1 equals 3. So that means it has 3 spin states, just minus 1, 0, plus 1. Now let's see more about the spin states of a proton. We have seen that a proton with the spin quantum number I equals 1 by 2 has only 2 allowed spin states. And these 2 spin states are degenerate in the absence of a magnetic field. Degenerate means they are having the same energy. And the 2 spin states are represented as plus 1 by 2 or alpha spin, and the other is minus 1 by 2 or beta spin. The one with the alpha spin is spinning clockwise and the one with the beta state is spinning anti-clockwise. So these are the 2 spin states of a proton which are having the same energy or degenerate in the absence of a magnetic field. Now, when we put this proton into an applied magnetic field, what happens? On applying an external magnetic field, the degenerate spin states split into 2 different states. One is of lower energy, that is with the spin plus half, which is aligned with the direction of the applied magnetic field. And the other is of higher energy with spin equals minus half, which is aligned in a direction opposite to the applied magnetic field. So proton with 2 spin states with plus half and minus half, they are degenerate or they are having the same energy in the absence of a magnetic field. But when we apply an external magnetic field, the magnetic moment of the spinning proton will be aligned either with the direction of the applied magnetic field or in a direction opposite to the applied magnetic field. And those which is aligned with the applied magnetic field will have a lower energy, that is with spin equals plus half, and those which is aligned against the applied magnetic field or opposite to the applied magnetic field will have a higher energy with spin equals minus 1 by 2. So that is the degenerate spin states split into two states, one of lower energy and the other is of higher energy. So that means there occurred an energy separation between the two spin states, which can be represented as delta E. The transitions between these two nuclear magnetic energy levels can be induced by electromagnetic radiation having a frequency that matches with the separation between the energy levels. That is, if an electromagnetic radiation having a frequency or energy that matches with the energy separation between these two states, then such a radiation can induce transitions between the magnetic energy levels, and such a transition between the spin states gives an NMR spectrum. This phenomenon is known as nuclear magnetic resonance and forms the basis of NMR spectroscopy. In all other spectroscopies like in rotational, vibrational and electronic, the transition between the corresponding energy levels will occur by the interaction of the molecule with the electromagnetic radiation. But in NMR, the transition between the nuclear spin states can be effected only in the presence of an applied magnetic field. Now let's see how quantum theory explains the origin of NMR spectrum and how the spin of a nuclei interacts with a magnetic field. First, let's see an expression for the magnetic dipole moment of a nucleus. We have seen that a charged spinning particle will generate a magnetic field, or such a particle will act as a magnetic dipole. And the resulting nuclear magnetic moment, vector mu, is oriented along the axis of spin, and this magnetic moment is proportional to the spin angular momentum vector I. Or we can write vector mu equals gamma into vector I, where gamma is the ratio of vector mu by vector I and is called the gyromagnetic ratio, or it is also known as magneto-gyric ratio. Now this gyromagnetic ratio or magneto-gyric ratio is a characteristic quantity of a nucleus, and it is given by gamma equals Gn into E by 2mp, where mp is the mass of the proton, E is the elementary charge, and Gn is another constant called the nuclear G factor. Now this is a unitless constant and it is characteristic of each nucleus. For proton, the value of Gn is 5.585. The Gn values are usually determined experimentally, and it is positive for majority of the nuclei, and for proton it is 5.585. So equation 1 can be written as vector mu equals Gn into E by 2mp into vector I. The magnitude of the spin angular momentum vector I equals root of I into I plus 1 into h cross. Therefore, the magnitude of the nuclear magnetic moment is absolute value of mu equals Gn into E by 2mp into root of I into I plus 1 into H cross. Now this can also be written as mu equals Gn into EH cross by 2mp into root of I into I plus 1. On further simplifying, we get mu equals Gn beta n root of I into I plus 1. Now this quantity beta n equals EH cross by 2mp. This is called the nuclear magneton. H cross can be written as h by 2 pi. So this can be written as beta n equals EH by 4 pi mp. If we substitute the values for E, the elementary charge, H, the Planck's constant, Nmp, the mass of the proton, you will get the value of beta n as 5.05 into 10 raised to minus 27 joule per Tesla. And this is called the nuclear magneton. So we have got an expression for the nuclear magnetic moment of the nuclei, that is mu equals Gn beta n in the root of I into I plus 1, where Gn is called the nuclear G factor, beta n is the nuclear magneton, and we also had another term, that is gamma, which is called the gyromagnetic ratio or the magnetogyric ratio. Now let's discuss the quantum theory of NMR. We have got an expression for the nuclear magnetic moment vector mu. Now when we put this magnetic dipole, that is the spinning nuclei, into an external magnetic field, then the nuclear magnetic dipole will interact with an applied magnetic field. Let the field applied be B0. Then the potential energy of interaction between the magnetic dipole and the applied magnetic field along a particular direction. Let's take it as the Z direction, as given by E equals minus vector mu into B0. Here E is the potential energy of the interaction of the magnetic dipole mu and the applied field B0. Now we have already got an expression for vector mu, and that is mu equals Gn into E by 2mp into vector I. So substituting in equation 3, we get E equals minus Gn E by 2mp into V0 into I, where I is the spin angular momentum vector. Now if we consider only one particular component of the spin angular momentum, for example the Z component. So if Iz represents the Z component of vector I, equation 4 can be written as E equals minus Gn E by 2mp into V0 into Iz. Here we have omitted some intermediate steps to make it more simple. So the potential energy of interaction between the magnetic dipole and the applied magnetic field is given by E equals minus Gn E by 2mp B0 into Iz. However, only certain orientations of vector I are allowed by quantum mechanics. So the possible values of the Z component of vector I is given by Iz equals mi into h cross, where mi is a quantum number and its values range from minus I to plus I. Or we can say that Iz is quantized along the direction of a magnetic field with the possible values mi into h cross. So we can substitute the value for Iz in equation 5. So we get E equals minus Gn E by 2mp into B0 into mi into h cross. E H cross by 2mp is beta n, the nuclear magneton. So we can also write E equals minus Gn beta n B0 Mi, where Mi equals minus I plus 1 etc. up to I minus 1 I. So this is the potential energy of interaction between the magnetic dipole and the applied magnetic field. E equals minus Gn beta n B0 into Mi. Therefore, the separation between the two energy levels is given by absolute value of delta E equals absolute value of Gn into beta n B0 into change in the magnetic quantum number delta Mi in joules. Here the modular sign indicates we are considering only the positive values. For a magnetic dipole transition, delta Mi equals plus or minus 1. So in the above equation, if delta Mi equals 1, then we can write delta E equals Gn beta n B0 joules, where B0 is the strength of the applied field. So from this, we can see that the separation between the energy levels delta E depends upon the strength of the applied field. We have seen that when a spinning proton is irradiated with an electromagnetic radiation that matches the energy separation between the two states, then the transition between the two states occur and will result in an NMR spectrum. And the value of this difference in energy delta E is given by Gn beta n B0 joules. The frequency nu at which the transition between the spin states takes place is given by nu equals delta E by h. So that is equal to Gn beta n B0 by h hertz. This represents the Bohr frequency condition, and this is the fundamental equation of NMR, and this equation shows that the frequency of the electromagnetic radiation that is required to induce a transition between the two states depends upon the strength of the applied field B0. Gn, beta n and h are all constants, so the frequency of electromagnetic radiation will depend upon the strength of the applied magnetic field B0. This equation represents the resonance condition at which the energy is absorbed by the nucleus, thereby exciting it to the higher energy state and finally results in an NMR signal. Only an electromagnetic radiation having a frequency nu that matches with the energy of separation between the two states can induce transition between the spin states and result in an NMR spectrum. And that's why NMR is known as nuclear magnetic resonance. The selection rule is delta Mi equals plus or minus 1, and that means the transitions between the adjacent levels are only allowed. For practical reasons, we usually apply magnetic fields in the order of 1 to 5 Tesla. So if B0 equals 1.4092 Tesla, and for proton, the nuclear G factor Gn equals 5.585, the nuclear magneton beta n equals 5.05 into 10 raised to minus 27 joule Tesla inverse. Then the frequency is nu equals Gn beta n B0 by h. So if we substitute these values in this equation, we get the frequency as 60 megahertz, and this corresponds to the radio frequency region of the electromagnetic spectrum. So we can say an NMR spectrum is obtained as a result of interaction of the magnetic nuclei with the radio frequency waves of the electromagnetic spectrum in the presence of an applied magnetic field. This is the quantum mechanical description of nuclear magnetic resonance spectroscopy.